This video will discuss the answers and a bit of the concepts behind number 26 through 55 of the multiple choice of the 2013 released International Chemistry Exam. So starting with number 26. So this is Le Chatelier's principle. The answer is E. They are asking for which of the following reactions would the stress of decreasing volume cause a shift toward product. If we remember that only substances in the gaseous state are stressed by a change of volume, which will have a consequence of a change of pressure. So we want to look for the side of the reaction where there are fewer moles of gaseous product. If we're trying to shift to product, that will relieve this stress. And the answer with less moles of gas on the product side, the only choice is E. You have 2 moles of gaseous reactant to 1 mole of product. Otherwise, there's equal number of moles, like in the reactant and product side, or more moles of gas on the product side, like in D. So E is the only choice. All right, number 28, this is Dalton's law of partial pressures. So what you have to make a note of is that the nitrogen is in a 2-liter sample. They both are showing 1 atmosphere pressure at the same temperature, and then they're put both into 1 liter. The argon will continue to exert a pressure of 1 atmosphere, but since you are decreasing the volume in half of the nitrogen, the pressure should double. So the nitrogen will show 2 atmospheres. So adding, it's a total of 3, which is choice C. Entropy is the disorder, better referenced as increased positional probability. So when we're asked which process has the greatest increase in entropy, the best would be where the product side has more moles of gas versus something like solid. And that is shown to us in E. We are producing a gaseous product from a solid reactant. So E is the best choice. Number 30. If we remember that we can find a new K value if we understand the reaction changes that we are making. So they're giving us this reaction that has a capital K, or an equilibrium constant of 95. So if we observe, what we've done is we have reversed this reaction to get this. And the K of the reverse reaction is the inverse of the forward. So definitely we're going to be putting 95 in the denominator. But the question is, well, what about the other thing we're doing? So the other thing that we've done besides reverse it is multiply all of the coefficients by 2. So then the K of the new will have whatever we've done as an exponent. So the new K will be the inverse of the old K squared, and that is choice E. Okay, 32. So the rate of the reaction will be a result of this equation, right? So your reactants raised to some power, which is their order. So if we change anything here, the concentration of reactants, we're going to change rate. But we can't forget the factors that impact K. So K is impacted by temperature and activation energy. So the choice for 32 is E. That if you change the partial pressure of hydrogen, you must have changed the amount of hydrogen to be able to do that. If also the C2H4 wasn't changed, it's also in the gaseous state. So to change just the partial pressure of it, you must have changed the amount of it, which of course will change rate. You are changing the particle size of the catalyst, which of course will then help the catalyst to come more into contact with the reactant in its step of the reaction mechanism. So that will change rate, and temperature, which impacts lowercase k. So E is definitely the choice. All right, continuing onward. 33. All right, you are making 100 milliliters of a molar sodium chloride solution. And if we remember, turn that up to make it a little bit better, molarity is mole of solute per liter of solution, which is the volume of the solute and the solvent. So to account for that, a volumetric flask is best. Remember, a volumetric flask is really just utilized to make molar solutions. There's just one marking on the neck, which in the case of 100 mils would show you when you've reached perfectly 100 mils of solute and solvent. So D is the best choice, hands down, to make a molar solution. All right, now jumping to 37. Okay, if we remember, enthalpy of formation is the amount of heat required or released to make 1 mole of your substance from its elements that make it up in their standard state. So we are given this reaction, and they're asking us for the enthalpy of formation of ammonia. So we are making ammonia, and we want to make 1 mole of it, and the elements that make it up are nitrogen and hydrogen. Both of those are diatomic, and gaseous state would be their reference form at standard state reference form. We remember standard conditions. Reference form would be where the enthalpy of formation is 0 for these guys. So to make 1 mole of this, we would need 1/2 mole of nitrogen and then 3/2 moles of H2. All right, so what we've done is we've flipped this reaction to get this. So then we know the enthalpy of this reaction will have the opposite sign, where in this direction it is endothermic, in this direction it will be exothermic. But what we've also done is halved. We've multiplied the coefficients by 1/2 or divided them by 2. So that means we have to do the same here. So then the enthalpy of reaction, which represents the enthalpy of formation of ammonia, because we're making 1 mole of it from its elements in their reference form, it is -46 kilojoules per mole of reaction. And that is choice B. 38. So we are being asked to think your way through a lab procedure in that we would follow to determine the percent of silver in some kind of solid sample. So you have a certain mass of sample that has, we assume, elemental silver. We're doing something to create the ion form, making it aqueous, then adding some source of chloride to precipitate it. We then filter out the precipitate, dry it, and then through knowing the mass of silver chloride that we collected, we'd be able to backtrack to find the percent of silver in the solid. The answer to this is E. So it's asking, not doing one of these would cause an error. And so these are the full wording. But, okay, if we didn't mass the filter paper, well, at the end of this, when you collect the silver chloride on the filter paper, you're going to mass the filter paper and this. So to be able to get the mass of the silver chloride, you need to mass the filter paper alone. So if we didn't do that, we'd be in trouble. And we can't just mass another sample of filter paper, because even if they're from the same box, who's to say that they're exactly all the same? Okay, measuring temperature. Temperature we know can affect solubility, but I'm sure that we, prepared this to provide ample amount of solvent to fully dissolve all this there. Nah, measuring temperature isn't going to help or impact, any kind of mass measurements. Washing the precipitate. So once we filter this, we want to make sure that we wash it thoroughly with water to be sure that any extra ions haven't been trapped by the filter paper, or any excess ions have been washed out. So we definitely want to do that, because we could end up with more mass there than is really the silver chloride. Then, once you've caught it in the filter, you of course want to make sure that you're heating the filter paper or drying it, and make sure that it's drying to constant mass to drive away all of the water. So these three must be done to help ultimately determine an accurate percent of silver in the solid sample. All right, number 40. So this is asking about strength of base. We are told that this reaction is favoring right, spontaneous to the right. So we know our K would be much greater than 1. We are going to have more product than we do reactant. Well, bases accept the hydrogen ion. So in this reaction that's shown, both carbonate and sulfate are acting as bases. This in the forward direction and this in the reverse. The stronger base will keep a hold of the hydrogen ion. That is its job. It accepts the hydrogen and holds on to it. So if we have more product, that means this is the stronger base. If the sulfate were stronger, then we'd have more reactant. 41 is just dealing with balancing. I checked it really quickly to see if this was an oxidation reduction reaction, and no, that's not what's involved here. So you just have to do your balancing, and we get a coefficient of 2 on the water. And choice B. All right, continuing onward. 42 deals with the forces that will be holding fluorine, HCl, and HF together. The greater the intermolecular forces, the greater the boiling point. F2 would just be single bonded, non-polar, only lone dispersion, holding fluorine samples together. HCl is polar, LDF and dipole-dipole, but HF also has the formula requirements to also have hydrogen bonding. So in order from left to right, these are stronger intermolecular forces, so this will have a greater boiling point than this, All right, and 43. So we have to find the gas that we're collecting over water that doesn't react with water, and hydrogen is the only one. Choice B and D, those are nonmetal oxides, and they will create oxyacids when react with water. And then C, strong acid, that's going to ionize with water. And then here's our classic weak base, which will behave as a base, creating ammonium and hydroxide. And so when you're trying to just purely collect your gas, when the other gases are traveling B through E through water, they'll end up reacting, thereby lessening the amount of gas. And so we won't be able to really analyze it. Hydrogen's the only one. 44, that is seeing if you remember how to calculate empirical formula. They're trying to find the formula of the hydrate. So we want to find, given what we're given, how many moles of sodium sulfate and how many moles of water do you ultimately have separately when you heat this. So when you heat a hydrate, you will drive off just the water. So they're telling you the mass of the hydrate than the mass of the anhydrous, or what is left after you remove water. So if you subtract, you'll get 1.80 grams of water. Look how great and cooperative our math is. So divide by 18, that's 0.1 moles of water. And look, dividing by the formula mass, the amount of anhydrate that you have, or dehydrated hydrate, it's 0.01. Dividing by your smallest amount, you get a 1 to 10 mole ratio. And so that is choice D. 45, we are asked to find the Ka. We're told we have a 0.1 molar weak acid, and it's giving a pH of 4. So, setting up our ice table, and even though can't use a calculator, you know if a pH is a whole number with 0 after the decimal point, then this is the inverse log of the negative pH. And so, plugging this in for our x, but that also will be the conjugate base, divided by 0.1, we are applying the 5% rule, and then multiplying, this of course will give us 10 to the negative 8th, we would add our exponents, divided by 0.1, just be careful, 1 times 10 to the minus 7, which C is our choice. Then, 46, anytime we're dealing with calorimetry, we just need to think Q equals MC delta T. Now we could reason our way through this, truly. But just to, set up the math, if they're put into contact, we know that whatever's at the higher temperature will lose heat, whatever's at the lower will gain. But to make these equations equal, we need to make the lost side negative, just to make both sides positive in the end. So, working through, we would round out our final temperature to be 33. And take a look, I had to embarrassingly, I guess, do long division. But, it's cooperative math. I wonder if so many of you could just do that mentally. But we could just reason our way through this. You have 50 grams at 40 and 30 grams at 20. If we had the same mass that we're adding together, then we would end up at 30 degrees Celsius at a temperature right in between. But we have a little more of a greater mass of water, so therefore we're going to end up greater than 30, but not very much. So given our choices, I think we could reason our way that D would be the choice without even doing the math, and we would be correct in that. All right, 47. 47, I'm surprised they did not eliminate this. It deals with isomers, and that's not really expected of us. An isomer is something that has the same formula but different structure. This is dealt with in organic chemistry, and we're not held accountable for that any longer. 48. So, remember when we use KHP, we had to keep it in the warming oven, and that's because it absorbs water. Well, it's a 1-to-1 mole ratio of KHP to NaOH, but even if we didn't remember that, water, if we did not dry it, would be in this KHP, which would give the perception of a greater number of moles of NaOH that needed to react with it. So the greater the mass, the greater the number of moles, which would have led to a greater sodium hydroxide calculation, but it's because of A, not because of B. Because of A. All right. And 49. So this C5H12 would be nonpolar. And remembering like dissolves like. So we want to choose of the given which would dissolve the most. So which of these is nonpolar? Well, hopefully we can get rid of the ionic, which is the most extreme example of polarity, being separate ions. Water, of course, polar. Carbon tetrachloride. Remember, that's one of the molecules that is good for us to just know. Oh, these are chlorines. Along with methane. So this non-polar. So this could be, and this, of course, is polar. So no. But what about silicon dioxide? Well, that is, excuse me, a covalent network solid. That's quartz. Oh my gosh, that is not going to be soluble in water or in nonpolar. So officially we'd say this is nonpolar, but we know that these are networked. All of these are bonded. This is an extraordinarily strong solid, extraordinary intermolecular forces or particle attraction. No way is the solvent going to be able to entice molecules or atoms away. So, no. this carbon tetrachloride would definitely be the choice. Choice D. All right. And 51, we need to employ the method of initial rates. So if you want to take a look at my work, I just thought through it. So comparing experiment 1 to experiment 3, you double the concentration of X, but there's no change on rate. That means X is 0 order. Experiment 3 to experiment 2, you are doubling the concentration of Y, and the rate increases 4-fold. That means Y is 2nd order. So we get this equation, which of course can be rewritten that way. So B is the choice. 52. Okay, so when I look at this reaction, first, what is my sign on entropy? And entropy is, we are looking at the moles of gaseous reactant compared to moles of gaseous product. I'm actually decreasing entropy. I have less moles of gas, so I know my change in entropy is negative. So that rules out A and B. I know for sure. Now what am I doing here? I am satisfying one of the main driving forces. We are making water. That is very, very low in energy and enthalpy. So we know it's going to be exothermic. So our delta H is negative. So that definitely leads us to D. And we know it is a driving force. When we have a driving force, it's going to be spontaneous. So that means delta G is negative. So D would be the best choice. 53, it is another empirical formula, but with elements. So if 48% is oxygen, we would assume the rest from 100 is chromium. Getting moles, then dividing by your smallest amount, we get CrO3, which is the correct choice of C. All right, ionic compounds. So what helps them be so soluble? 2 things. We know like dissolves like, so it is water molecules surrounding each ion, which would create the ion dipole force. That would be Roman numeral 2. But we're going from solid to aqueous ions that are now exchanging places. We're increasing entropy, so it would be 3. So choice D, Roman numeral 2 and Roman numeral 3. All right, vapor pressure. Vapor pressure, the pressure a vapor exerts on a liquid it evaporated from. Vapor pressure is related to temperature and the intermolecular forces of the liquid. The greater the temperature, the greater the vapor pressure. The greater the intermolecular forces, the lower the vapor pressure. So they're asking us which is true. They're talking about, making changes, but the only thing that changes vapor pressure is a change of temperature or doing something to change the intermolecular forces of your liquid. So E is the choice here. So when we change temperature, we are going to change vapor pressure. So that's what makes A untrue. And then B, C, and D talk about making changes that then change vapor pressure. But the only thing that changes vapor pressure is a change of temperature. So that's not true. And then, volume, nope. It depends on temperature and intermolecular forces. Thank you.